We're going to continue in Chapter 5 by talking about lift. And lift is an important concept. It helps us to differentiate between any model that we have for classification and comparing that with the naive model, which would just be randomly assigning individuals to either a 0 or a 1. And this becomes important when the cost of making errors is not the same. So imagine we're going to issue credit cards to people. We have application information that they've submitted, and we have two choices. We can either issue them a card or not issue them a card, just to keep things simple. So those that we decide we're going to not issue a card to, we could say, well, there's a chance for making an error, and the error is that these would be good customers and they would pay back their money that they borrow. They might pay some interest, hopefully they would, and if we don't issue them cards, then the cost of that is the transaction fees that we could collect and also any interest that they might pay. So that's an error. But the other error is if we decide that somebody is going to be a good customer and we send them a credit card and say, here's a credit limit, and they need some cash, but they're not going to pay it back. So they run up the card to the credit limit, and then they skip town, and you never hear from them again. In cases such as this, we are going to be willing to tolerate a greater error if we can find those people that will not pay back their debts and incur larger costs to the company. And this can be used, this tool, this lift chart can be used for determining that. So we have two different measures that we're going to talk about. One's called sensitivity and specificity. And sensitivity is the proportion of the ones that are classified correctly. Specificity is the proportion of the zeros that are classified correctly. That's one way to think of this. And the other is the false positive rate, which is the proportion of the predicted ones that are not actually ones, and false negative rate, which is the proportion of the predicted zeros that are not actually zeros. So these turn out to be very closely related, but they're not the same measures, although oftentimes they are erroneously used one in place of the other. So we can look at these things on a graph. If we put the sensitivity on the y-axis and the specificity, or rather 1 minus the specificity on the x-axis, notice that here they're saying 1 minus the specificity is the same as the false positive. That's not the case. What really is going on here is they're saying if you put the false positive here and the true positive right here, then you would have similar things. But these are not actually the same thing. So we're going to actually cross out the true and the false positive, because if we did have the true positive and the false positive on the chart would actually potentially be different. But the idea here is if the specificity is 100%, that means that we have correctly classified all of the zeros. That's going to put us somewhere on this line. And if the sensitivity is 100%, that means we've classified all the ones correctly. That's going to put us at this point right here. So if we let the sensitivity go down, we're going to stay on this line here. So the best curve we could see in terms of a receiver operating characteristic curve, or an ROC curve, is this one that I've got drawn in right here. And so what we observe is almost never going to be exactly like that. If it is the best thing here, that means we perfectly discriminated between the ones and the zeros. But that's the gold standard, so that's what we're going to compare it to. This is actually a tool that can be used to compare different models, and you can look at the ROC curves for competing models, and the one that's closest to the ideal is going to be the best fitting model. Lift and lift curves are very useful tools for identifying the most important class. For example, if you worked at the IRS and it was your job to determine who was going to be audited, you have millions and hundreds of millions of people in the United States that you could potentially audit. You can't very well audit all of them, and most of them are probably not cheating on their taxes. So you want to be able to identify those who are most likely to be cheating and audit those. So a lift curve is something that would help you to do that. And the idea here is to estimate the probability that people are going to be considered cheating on their taxes, and then compare the proportion of that rare event that you would get based on the model that you are using to no model or random pick. And by that I mean if you were looking at all of your potential taxpayers and you said, well, I don't have any idea which ones are in need of being audited, so I'm just going to randomly select, that would be the no model or the random pick. And so we want to compare how our model would do to that one, and the lift curve tells us how that works. We can see what a lift curve looks like by putting the portion of the total number of records that we might sample on the x-axis, and then on the y-axis we would say what is the lift, or in other words how many times more likely are we to identify the class of interest if we take, say, the top 10% or the top 20% or the top 30%. So this curve here is comparing the model that we've used to fit to the baseline model, or just the random model, which would be represented by a lift of 1. So this says here for 20%, if we took the top 20%, we would identify twice as many fraudulent taxpayers than if we just randomly were to select. This brings us to the point where we can talk about asymmetric costs. And one way to think of asymmetric costs is really, instead of thinking about the cost of making a misclassification, we could say, well, what's the benefit of making the correct classification? So let's look at this example. We want to send an offer to 1,000 people, and the average response rate is only 1%. So that's pretty rare. The naive rule says, let's just classify everyone as a 0, because that will give us an error rate of only 1%, and that sounds pretty good, doesn't it? With a 1% average response rate, let's say of these 1,000 people, then there are 10 that would respond affirmatively, and the remainder, 990, that would not respond. And we can come up with a data mining procedure that correctly classifies 8 of those 10 ones as ones, but it does it at the cost of misclassifying 20 of the zeros as ones and 2 of the ones as zeros. If that's the case, we can look at the confusion matrix, and we have 990 actual zeros, and we're predicting that we have 970 zeros correctly, and 20 of these zeros we're classifying as a 1. So in total, we're predicting that there's 28 ones, and 8 of those are correct, 20 are not correct, and we're predicting 972 zeros. 970 are correct, and 2 are not correct. So that gives us an error rate of 2 plus 20, or 22, divided by, should be divided by 1,000, or 2.2%. So that's considerably higher than the naive rate of 1%. And so we have to ask ourselves the question, is it worth it? And in this situation, you would say, or the naive rule would predict everyone to be a 0, and so we would not send out any offers. And if we don't send out any offers, we're not going to get any business or any responses. So let's look at the profit that we would get from a 1. And in this case, we'll say if it's a 1 and we identify it correctly, we make $10, and it costs us $1 to send out each of the offers. So if we use the naive rule and everyone's classified as a 0, then we don't send out any offers. It doesn't cost us anything, but we don't make any money. Using the data mining procedure, we send out 28 offers, and 8 of those respond with a profit of $10 each. 20 don't respond, so that costs us $1 each, and 972 get nothing. So we have $80 here. That's what we bring in, and we have to pay $20 to do that. And notice this is the profit, so we're really bringing in $11 to offset the $1 for sending it out. Oftentimes, however, it's difficult to know exactly what the costs and the benefits are going to be, and one way to deal with that is to look at the ratio of those things. And so we would say Q1 is the cost of misclassifying an actual 1, Q0 would be the cost of misclassifying an actual 0, and so what we want to do is minimize the ratio of Q1 over Q2, and that's going to be the same as minimizing the average cost per record. And in the business vernacular, it's actually better to talk about everything being in terms of costs, so opportunity costs of lost business instead of benefit from sell. That gives us greater applicability, but it's really the same thing. So what happens when you have more than 2 classes? Well, it gets to be very messy very quickly because there are many misclassification costs, and usually that's going to be too many for us to work with, and that's actually okay most of the time because typically there's going to be one class that's really of interest, and so every other class qualifies as not being that class. Oversampling and asymmetric costs. Sometimes we have rare cases. We've actually been talking about some already. And when we have that with asymmetric costs, then, and that's typically what happens, then we can do something called oversampling that gives us more information to use in our model to identify those rare cases. So we would do that in the training data set so that the model actually kind of knows what to look for. And the idea would be to use 50% ones and 50% zeros in order to build the model. And in what follows, we have 3 different scenarios where we have equal costs of misclassification, 5 times the cost of misclassifying one over the other, and oversampling that allows us to incorporate those asymmetric costs. So here's the case where we have data, we have X's and O's, we have equal costs here, and so if we draw the line where you see it, we're going to classify everything correctly except for this one thing. Now if the cost of misclassifying an O is higher, 5 times higher than an X, that's going to change the classification scheme, because now we've got these O's that we want to make sure are classified as O's, and they're 5 times more expensive than the X's. So we have 2 X's up here that we are going to misclassify. We don't really care about that. What we really want to do is get the O's correctly. And it turns out if we use oversampling, which says let's just repeat the O's that we have here, so instead of 1, let's say we got 5 because that's the cost, then we see that we're really doing the same thing as this oversampling here. So one way to do this oversampling would be to separate the responses from the non-responses and then randomly assign half of the responders to the training sample plus an equal number of non-responders, and then the remaining responders go to the validation sample with the rest of the non-responders. This overrepresentation of the responders in the training data set is actually very good because it tells the model what it looks like for a responder. And so the model learns what the characteristics are of responders. When we can't say whether we should classify one way or another, and we talked a little bit about that earlier, that's a time when we need to bring in an expert, a domain expert, somebody familiar with the industry or the data, and have them review it. In this chapter we talked about the metrics that are important for comparing data mining models and choosing the right model and comparing to baseline models. Well, the major metrics that we talked about were confusion matrix, error rates, and the predictive errors. When the costs of errors are asymmetric, then we discussed how to deal with that, and we talked about oversampling and when we can use that. And finally, it is the validation data that we are going to be using to compute all of the metrics that we're making decisions based on. So that's what I've got for chapter 5, and we will see you guys